This session is on the concept of elasticity. Elasticity, in the economic context, refers to the sensitivity of the dependent variable to changes in the independent variable. A relationship is sensitive and therefore elastic if a relatively small change in the independent variable results in a relatively large change in the dependent variable. For example, if a few additional minutes of study time per week resulted in a 20-point increase in your test scores, the relationship between study time and test scores would be elastic. Or, if you run just a few more yards a month and your weight falls by an additional 10 pounds, that relationship is elastic. On the other hand, let's say that you study an additional 10 hours per week, but your test scores only go up by 1 point. The relationship between study time and test scores would be insensitive and therefore inelastic. Or, if you run an additional 20 miles a month and your weight only falls by 1 pound, that relationship is also inelastic. The types of elasticities we'll be studying in this module are the price elasticity of demand. This, of course, refers to the relationship between the change in the price of a good and the resulting change in quantity demanded. The price elasticity of supply. This obviously refers to the sensitivity of the relationship between the price of a good and the resulting quantity supplied. The income elasticity of demand. This refers to the sensitivity of the relationship between a consumer's income and the quantity of a good he purchases. And the cross-price elasticity of demand. This measures the sensitivity of the relationship between the price of one good and the quantity demanded of a different good. Let's start with the price elasticity of demand. Look at these two demand curves for a moment. Which of these do you suppose represents the more elastic relationship? As it turns out, demand curve B is the more elastic of the two. That's because a relatively small change in the independent variable, price, produces a relatively large change in the dependent variable, quantity demanded. Remember, when we plot supply and demand curves, for some reason, the independent variable price is traditionally placed on the vertical axis. By the same reasoning, demand curve A is less elastic, or more inelastic. Here, you can see that a relatively large change in the independent variable price produces a relatively small change in the dependent variable quantity demanded. So now, let's have a look at our first application of the concept of price elasticity of demand. If you were selling a product, how might you increase your total revenue? Would you increase your price? Although you'd increase the revenue per unit sold, the number of units you'd sell would decrease. Or, if you'd lowered your price, you know that the revenue per unit sold would decrease, but you'd sell more. The answer to this question is, it depends. It depends, as you might have guessed, on the price elasticity of demand. Let's examine what the price elasticity of demand has to do with total revenue. Recall that total revenue is the product of price times quantity, the number of units sold. Okay, so here's a demand curve. This demand curve is not particularly elastic, in which case it would be more flat, or particularly inelastic, which would cause it to be steeper. We'll just kind of randomly select a price-quantity combination. This one seems pretty convenient. As it turns out, when we multiply price by quantity, we get the area of this box. We might just call this the total revenue box. notice that on the less elastic demand curve, the higher price results in a larger revenue box. For the more elastic demand curve B, it's the lower price that produces a larger revenue box. When you think about it, this makes perfect sense. When the demand for an item is inelastic, you can increase total revenue by increasing the product's price. That's because an inelastic demand means that consumers are not responsive to price changes. You can raise the price of the product, but consumers will buy it anyway. You won't lose that many customers. The gain in revenue per unit from the price increase will more than offset the loss in quantity demanded. But if you lower the price of the product, you'll lose revenue per unit, but you won't gain many customers. The loss in revenue per unit will more than offset the increase in quantity demanded. On the other hand, if the demand for a product is elastic, an increase in the product price will cause consumers to bail like rats from a sinking ship. Any gain in revenue per unit sold will be more than offset by a loss in sales. But if you lower the price, although you'll lose revenue per unit, consumers will be very responsive and you'll attract a lot of new customers. The gain in units sold will more than offset the loss in revenue per unit. You can actually increase revenue by lowering price when the demand for your product is elastic. The orange box down at the bottom succinctly summarizes this concept. If the demand for a good is inelastic, total revenue fluctuates directly with price. If the demand is elastic, total revenue fluctuates inversely with price. This is good information, but remember, firms want to maximize profits, not necessarily total revenue. But how would we know if the demand curve for a good is elastic or inelastic? For example, how elastic or inelastic is this demand curve? You can see that it's kind of steep and therefore might be inelastic. But how inelastic is it, if at all? We can determine this by computing the coefficient of price elasticity of demand. That's a number that'll tell you how elastic or inelastic a relationship is. We'll use this expression to represent the coefficient of price elasticity of demand. E will represent elasticity. The superscript P will represent price, the independent variable. The subscript D will represent demand. Technically, though, the dependent variable is quantity demanded, not demand. Here's the formula for computing the coefficient of price elasticity of demand. It is the ratio of the percent change in quantity demanded relative to the percent change in price. Just a technical point here. The formula is actually the absolute value of the ratio. That's because the inverse relationship between price and quantity demanded will cause this ratio to be negative. So by considering the absolute value, we can dispense with the negative signs. So if this ratio, and that's the absolute value, remember, is greater than 1, that means that the quantity demanded would change more than did the change in price. Thus, the relationship would be considered elastic. And, as you will recall, if the relationship is elastic, a change in price will cause total revenue to move in the opposite direction. As indicated here, if the price of this good increases, total revenue will go down. On the other hand, if the ratio is less than 1, that means the percent change in quantity demanded would be less than the percent change in price. Thus, the relationship would be considered inelastic. And of course, an inelastic relationship would cause price and total revenue to move in the same direction. As it turns out, If the ratio is equal to 1, that means the change in quantity is exactly proportional to the change in price. In this case, the relationship would be known as unit elastic. Notice the effect of a price change on total revenue when the relationship is unit elastic. Whether the price goes up or down, because it is exactly offset by a change in quantity demanded, total revenue will remain constant. We'll see an example of this in just a little while. Let's consider one more thing before we move on. Computing the coefficient of price elasticity of demand, of course, requires computing percentage changes. But computing percentage changes can be tricky and confusing if you don't understand them intuitively. Let's do this little exercise in case you were absent that day in 6th grade when you went over computing percentage changes. Check out this grid. As you probably already know, a change from 1 to 2 is a 100% change. Anytime something doubles, it's a 100% change. But the change from 2 to 3 is only 50%. And the change from 3 to 4 is 33.3%. Even though we're only moving one increment each time, the percentage change from increment to increment varies, dependent upon where we are on the scale. And if that's not bad enough, watch this. When we're moving down the scale, the value of the percentage change is different from increment to increment from when we were moving up the scale. You should do yourself a tremendous favor and compute the percentage changes going each way from 1 to 10 and from 10 back to 1. Use this formula for computing percentage change. The new value minus the old value divided by the old value. Now that's going to give you a fraction. To turn it into a percentage, multiply it by 100. This quirky feature about percentage changes, and I'm talking about the fact that the percentage change from increment to increment along the scale not only depends upon where we are in the scale, but also in which direction we're moving. This is going to affect the way we compute the coefficient of price elasticity of demand. Okay, so we saw this graph a little while ago. This is your typical demand curve. It has a 45-degree slope. It's not particularly elastic or inelastic. And here's a demand schedule that would produce such a demand curve. Let's use this demand schedule to compute the coefficient of price elasticity of demand. We'll label the endpoints of this line segment in this way. We will label the blue price quantity pair P1 and Q1 respectively, and the red price quantity pair P2 and Q2 respectively. P1 would be the first price, P2 would be the new price. Here's the formula again. Using our formula for percentage change, new value minus old value divided by old value, then if the new quantity demanded is 1 and the old quantity demanded is 10, the percentage change in quantity demanded would be minus 0.9 multiplied by 100, and that would give us minus 90. Pause the video and verify this for yourself. Now let's do the same thing for price. When the new price is 10 and the old price is 1, the percentage change in the price would be 9 divided by 1 multiplied by 100, which would equal 900%. Again, pause the video to verify this. The coefficient of price elasticity of demand for this line segment would therefore be minus 90 divided by 900, which is minus 1/10. And since we're looking at the absolute value, then the coefficient of price elasticity of demand would be 1/10. 1/10 is less than 1. So despite the fact that this straight line 45-degree demand curve is not particularly flat or steep, the coefficient of price elasticity of demand indicates that it's highly inelastic. But now, let's try moving in the other direction. Rather than moving down the schedule, like we did in the previous computation, let's move up the schedule. You remember with our little exercise in computing percentage changes, percentage change is dependent not only upon where we are in the scale, but also the direction in which we're moving. Let's see if this change of direction will affect the coefficient of price elasticity of demand. Now that we have changed directions and are moving up the scale, the numerator in this ratio, the percent change in quantity, is now 900%. The denominator, the percent change in price, is negative 90%. This gives us a coefficient of minus 10. And since we're only considering the absolute value, the coefficient is 10. Pause this video and verify for yourself that these values are correct. Now that we're moving up the schedule and down the curve, as you can see over there on the right, we see that the coefficient of price elasticity of demand is 10, which would indicate that it is highly elastic, whereas when we were moving in the other way, it was highly inelastic. What's going on here? This is obviously due to the fact that percentage change is dependent upon the direction. So we need to take directionality out of the computation so that we can see unambiguously the elasticity of this demand relationship. And we can do this by using the midpoints formula. Here is the midpoints formula. It's the ratio of the difference in quantity relative to the difference in price multiplied by the ratio of the sum of the prices divided by the sum of the quantities. The derivation of this formula and the reason behind its derivation is explained in the lecture notes section of Module 4, entitled, surprisingly enough, the midpoints formula. Make sure you read and understand that essay. With the midpoints formula, it doesn't matter which pair you define as the new or old set of values. You're going to get the same number. So I suggest that you again pause the video and plug in values into these expressions. First, let the blue set be the starting point and compute the coefficient. Then, let the red set be the starting point. You should find that in both cases, the coefficient of price elasticity of demand is equal to 1, which is exactly what you would have expected from this demand curve. Then give it the total revenue check. When price is 1, total revenue is 10. When price is 10, total revenue is 10. Price changes, but total revenue doesn't change. The characteristic of unit elasticity. By giving it the total revenue test, we confirm that this demand curve from one endpoint to the other is unit elastic. From one endpoint to the other, irrespective of where we started, the coefficient of price elasticity of demand is 1. But look at what's happening to total revenue as we move down the demand schedule, which is up the demand curve. When price rises from 1 to 2, and from 2 to 3, and so on, total revenue also rises, at least for a while. If total revenue rises when price rises, that means the demand is inelastic. But then, as we continue to move down the demand schedule, up the demand curve, further price increases lead to declines in total revenue. When price and total revenue move in opposite directions, the demand is elastic. These changes in total revenue indicate that even though this is a straight line demand curve, at the lower prices the demand is inelastic. When price is going up, you can see total revenue is going up. And at the higher prices, the demand is elastic. Price and total revenue are moving in opposite directions. Take a few seconds to look at the schedule and the demand curve on the right. Let's investigate this phenomenon a little more closely. We'll start by dividing this demand relationship into three segments. Here they are on the demand schedule. Note where they are located on the demand curve. Pause the video and take a few moments to use the midpoints formula to compute the coefficient of price elasticity of demand for each of these line segments. The elasticity of demand for line segment A is 2/9, which, because it's less than 1, would make it inelastic. For line segment B, the elasticity of demand is 1, which would make it unit elastic. Notice that at one endpoint on line segment B, when the price is 4 and quantity demanded is 7, total revenue is 28. On the other end, when the price is 7 and the quantity demanded is 4, the total revenue is 28. This is characteristic of a demand curve that is unit elastic. The price changes, but total revenue does not change. And for line segment C, the price elasticity of demand is 9/2. Remember now, these are absolute values. A coefficient of price elasticity of demand of 4.5, which is greater than 1, means that this line segment is elastic. At the higher prices, this demand curve is more elastic. As the price goes down, it becomes less and less elastic and approaches unit elasticity. As the price goes down farther, the demand becomes inelastic. But now, let's take an even closer look at the relationship between price, total revenue, and the elasticity of demand. Here we see that when the price of this product, whatever it is, goes up from 1 to 2, total revenue also rises from 10 to 18. This direct relationship between price and total revenue indicates that the demand is inelastic. When price goes up from 2 to 3, total revenue goes up by a little bit less. This indicates that the relationship is still very inelastic, but not quite so much. As price goes up from 3 to 4, total revenue rises by even less, suggesting that while the demand is still inelastic, it is less inelastic or becoming more elastic. When price goes up from 4 to 5, total revenue rises, but just barely. The demand relationship now is just slightly inelastic. Now, look at this. When price rises from 5 to 6, total revenue doesn't rise at all, indicating that the relationship at this point has reached unit elasticity. Look at what happens after the price rises beyond the point of unit elasticity. Total revenue begins to fall, meaning that the demand relationship has become elastic. And as price continues to rise, total revenue falls by more, and even more, and this time by a whole lot. This shows us that if we wanted to maximize our total revenue, now remember, firms want to maximize profits, not necessarily total revenue. But if we wanted to maximize total revenue, we'd never want to price the product in the inelastic range of our demand curve because we could increase our total revenue by raising our price. Likewise, to increase total revenue, we would not want to price our product in the elastic range of the demand curve because we could increase our total revenue by lowering our price. This suggests that the closer the price comes to unit elasticity, the greater will be the total revenue. As you could guess, the point of unit elasticity on this straight line 45-degree demand curve will be right in the middle. Let's see what the total revenue will be if we price the product at the exact midpoint of the demand curve. We see that the unit elastic line segment on this curve is between the price of 5 and 6. The point exactly midway between these two boundaries, which we'll call the point of unit elasticity, is 5.5. We can easily interpolate that the quantity demanded at a price of 5.5 will also be 5.5. Because, of course, total revenue is price times quantity, the total revenue at the point of unit elasticity on this demand curve is 30.25. This is the point that maximizes total revenue. We saw a few minutes ago, when we were practicing using the midpoints formula to compute the coefficient of price elasticity of demand, that this straight line 45-degree demand curve had both an elastic portion at the upper end and an inelastic portion at the lower end. And the point of unit elasticity was right in the middle. In this example, at the beginning of this presentation, you were asked to guess which curve was more elastic and which was less elastic. You'll note that neither demand curve was referred to as an elastic demand curve or an inelastic demand curve. The question was which was more elastic and which was less elastic. That's because even a very steep curve like this one, which I referred to as relatively inelastic, will have both an elastic and an inelastic portion. This could be proven by computing the coefficient of price elasticity of demand for every price quantity interval on a schedule that would produce a steep curve like this when plotted out. If we were to do that, we'd find that the elastic portion at the top end of the curve is a very short line segment. The point of unit elasticity occurs in the upper portion of the line, and the rest of the line is inelastic. If the demand curve for a firm's product is relatively inelastic like this one, the firm will maximize its revenue by charging a high price. One caveat: remember, firms try to maximize profits, not necessarily total revenue. And a very flat curve, which we called a relatively elastic demand curve, will also have both an elastic and an inelastic portion. Only this time, the elastic portion of the line segment will be long, the point of unit elasticity will occur at the lower end, and the inelastic portion of the demand curve will be a short line segment. If the demand curve for a firm's product looked like this one, very elastic, the firm would maximize its total revenue by charging a low price. So, if the demand for a product is relatively inelastic, the revenue maximizing price, again, that's not necessarily the profit maximizing price, but the revenue maximizing price will be high. And if the demand is relatively elastic, the revenue maximizing price will be low. Armed with this information, we're ready to conquer the world as entrepreneurs. All we need to do is plot a demand curve for a product, and we'll know whether to charge a high price or a low price. But wait, how easy is it, in reality, to derive a demand curve? Turns out, it's almost impossible. Certainly, it's easy enough to plot a demand curve from a demand schedule, but how do you derive a demand schedule? Seemingly, you could just do a time series analysis on some data spanning back, say, a decade or two. You could look at the historical data and see that when the price of this product was $1 10 years ago, 10 units were purchased. Maybe 5 years later, when the price was $7, only 4 units were purchased. But how do you know these 2 points are on the same demand curve? It could be that in the time span in which these 2 data points were observed, in this case 5 years, there may have been some changes in the determinants of demand. It could be that these 2 data points, as valid as they may be, reside on 2 different demand curves, like this. Maybe there had been a change in consumer tastes and preferences, or possibly the number of consumers or consumers' incomes, something that could have caused the demand curve to shift to, say, the left. Or maybe there was a change in the price of a substitute or complement, or a change in price expectations during that period of time that might have caused the demand curve to shift to the right. Almost certainly, one or more of the determinants of demand will have changed, thus causing the demand curve to shift between the time in which these 2 data points were observed. The bottom line, in real life, it is extremely difficult, if not in most cases impossible, to accurately derive a demand schedule and thus plot a demand curve. But there is good news. All is not lost. We can make guesses about how elastic or inelastic the demand for an item might be by considering the determinants of price elasticity of demand. These are factors that will affect the way consumers perceive the item and therefore affect the way they respond to price changes. If an entrepreneur can estimate how elastic or inelastic the demand for his product is, he can determine whether to charge a high price or a low price. The first of these determinants, the first one that we will consider in no particular order, is the necessity of the item. Imagine a diabetic person walking up to the counter at a pharmacy to purchase this period's unit of insulin. The pharmacist tells him that since his last visit, the price of insulin has gone up by 5%. Is this diabetic going to say, "Oh, to heck with that, you can keep your insulin"? No, of course not. He's going to curse his bad luck and buy it anyway. The alternative is death. We can conclude that because insulin is so vital to the diabetic, he's going to buy it pretty much irrespective of the price. We know that a relatively inelastic demand would produce a steep demand curve. But would the demand curve for an item that is so vital as insulin for a diabetic be so inelastic that it would produce a curve that is so steep that it's actually vertical? We'd call this thing a perfectly inelastic demand curve. Well, it would seem at first glance to be so, but let's remember what makes a demand curve have a downward slope. 2 things: the income effect and the substitution effect. Even though, as in the case of insulin for a diabetic, there is no substitution effect, after the price reaches some point, there will be an income effect. People will buy less not because they'd rather do something else with their money. We can conclude, therefore, that the more necessary the item, the less elastic or the more inelastic the demand will be. This second determinant, the availability of good substitutes, actually consists of 2 variables. First, the quantity of goods that the consumers consider substitutes, like, say, Nikes and Reeboks, and the closeness of the substitutes. Now, Nikes and Reeboks are probably pretty substitutable, but what about Jordans and the Walmart brand sneakers? Both are sneakers, but most consumers don't consider Walmart sneakers a close substitute for Jordans. More substitutes gives the consumer more alternatives and thus allows him to be more responsive to price changes. This even more so if the substitutes are close or good substitutes, that is, very much alike. If the consumer doesn't want to pay a higher price, he can simply buy something else that's just as good. The third determinant of price elasticity of demand is the portion of the budget that is used up by the purchase of the item. We've already seen that for a straight line demand curve, the demand becomes more elastic at higher prices. But this is not just because of the quirky nature of percentages. There's also some real-life logic to it. Consider a piece of hard candy that you put in your mouth and suck on for a while. We used to call them jawbreakers. Those things used to cost 1 cent a piece. If I went to purchase one now and find that the price had risen by 100% to 2 cents, would I even give it a second thought? Would this affect my decision to purchase the jawbreaker at all? On the other hand, consider a house priced at $500,000. If the price rose by only 10%, that would be a $50,000 price increase. This just might indeed cause me to have second thoughts. So it's probably pretty obvious that the greater the portion of the budget that is used up by the purchase of the item, the more elastic will be the demand. The fourth and final determinant of price elasticity of demand is time. Implicit in every demand relationship is a time frame in which the consumer responds to price changes. The elasticity of demand for widgets at the campus bookstore over a period of 1 week will be different from the elasticity of demand for widgets at the campus bookstore over a period of 1 year. Why is that? Same location, same set of customers. The difference is that the longer time frame gives the consumer the opportunity to find alternatives. And as you know, the greater the quantity and quality of alternatives, the more elastic will be the demand. If the price of widgets at the campus bookstore went up, the students buying the widgets might just have to pay it. They wouldn't have much of a choice, especially if the instructor required them to have widgets by the end of the week. But suppose the instructor required them to have widgets by the end of the semester. The students would have time to find widgets on Amazon or eBay or some other place, maybe some bookstore like Barnes Noble or some other place. Bottom line, the longer the time frame over which the demand relationship exists, the more elastic will be the demand. Be sure to watch the second of this 2-part series on elasticity. The second video will cover the price elasticity of supply, something called the cross-price elasticity of demand, and the income elasticity of demand. A link to this video is in the description box below and in the to-do list in Module 4.